Okay, good morning students. Today I am starting a lecture series on solid state physics, and today we will discuss the basic property of matter, then solids, then what are the main category of solids, and then about crystals, and then basics of crystals. So firstly we will discuss a little bit about matter. Okay, so matter, it is made up of atoms and molecules. Okay, now these atoms and molecules are bound with each other with the help of some kind of chemical and physical bonds. Okay, the strength of these bonds will decide the phase of the matter. So depending upon the strength of the bonds, we can divide matter into solids and fluids. You can also see plasma. This is also one of the type of the matter. So without going into detail, I will confine myself to solid and fluids. Okay, these fluids can be further categorized into liquids, okay, then gases. See, what is the difference between solid, fluids, that is liquid, and gases? The difference is the strength of chemical bonds. Okay, in solids the chemical bonds are stronger, so the particles are confined, particles are tightly bound with each other. Okay, in fluids the particles are not tightly bound, so the fluids can flow, but solids cannot flow. In solids, the particles are tightly bound, but when you provide energy, you heat, you raise the temperature, then particle can vibrate about their mean position. Okay. Class, vibration about their mean position gives rise to various important physical property which we will discuss in the coming lectures. So in this lecture we will confine ourselves to the solids and its types. Okay, so depending upon the bond strength, solids, and arrangement of the particles, we can categorize solids into crystalline solids and non-crystalline. Okay class, non-crystalline solids are also called amorphous solids, okay, or glassy solids. Okay class, now we will discuss what are crystalline and non-crystalline solids. Okay, so now we will discuss the solids. So broadly these are divided into crystalline and non-crystalline, or you can call amorphous solids. Okay class, now we will see how crystalline solids are different from amorphous solids. First of all, the very basic property and most important property is periodicity. The atoms molecules in crystalline solids are arranged in periodic and definite fashion. So first property is definite and periodic. Definite and periodic arrangement of particles. Okay class, in this case, in case of amorphous solids, there is no periodic and definite arrangement. Basically this is a mixture. This is a mixture. Okay, so here in ideal crystal, the building blocks or constituent particles are also same. Okay, so the bonds, chemical bonds which bind constituent particles in the solids, those are of definite strength. So it gives rise to sharp melting point. Melting point in case of crystalline solids, this is sharp. Okay, what is the reason? Sharp mean to say at a definite temperature the bonds will break down and the solid will convert into liquid. There will be phase transition. Class, you know that solid, liquid, liquids and gas. Okay, these are the three phases of the matter, and to change one phase to another phase, we need to understand the impact of two very important thermodynamical parameter. One is pressure and another is temperature. So if we assume the pressure is constant and we raise the temperature or we give heat energy to the solids, then that energy will break the bonds, and bonds here are of equal strength. The chemical bonds are of same or equal strength. Okay class, so if bonds are equally strong, then we need to give a definite amount of energy, and when that is provided to the chemical bond, they break down. Okay, so the melting point is sharp. But in case of amorphous solids, bonds are not equally strong. Bonds are not equally strong. I want to say some of the bonds are weak and rest of the bonds are stronger comparatively. So if you heat up an amorphous solid, the weaker bonds will break down initially and then the stronger bonds will break down. It means to say the melting point in this case will not be sharp. Here the melting point is not sharp. Okay class, now we have discussed three important properties. The fourth one is related to the periodic and definite arrangement. Very basic fundamental first property of the crystals, that is periodic arrangement. Periodic arrangement. This was first property, and this periodic arrangement gives rise to anisotropy. Okay, so what happens in anisotropy? If you change the direction of observation, the physical property will change. Okay, so this is due to periodic arrangement. Let us take the case, this is a particle, this is another particle, and this is a two-dimensional crystal structure. You see, if we take this direction, then particles are present at this distance, let this is A, and if you change the direction, then the particles are not at a distance A. Let this is B, then this distance is not equal to A, neither equal to B. So this periodic arrangement and definite arrangement gives rise to change in physical property with change in direction. Okay. So now come to amorphous solids. In amorphous solids, I have told you this is a kind of mixture with no definite arrangement, no periodic arrangement. So these solids show same kind of physical property with change in direction. So simply I will say these are isotropic. And crystalline solids, these are anisotropic. So this is the very important and basic difference between crystalline and amorphous solids. Due to this periodic and definite arrangement, one more property you can draw, that is entropy. You know that entropy is the measure of degree of randomness. Entropy, this is measure of degree of randomness. So class, in crystalline solids, particles are arranged in periodic and definite arrangement, and definite arrangement leads to higher order. Particles are arranged in a definite and high order in case of crystalline solids. So randomness is less in case of crystalline solids. So here entropy is represented by S. This is low. Okay. And here the particles, there is complete choice, complete randomness, no any definite order. Randomness is high. So here the entropy is high. Simply you can understand it. Or one more thing, you can see here why randomness here is low, why definite order is there in crystalline solids. When crystals form, then amount of heat energy is released. Okay class, suppose you have a liquid and you have a solid in liquid form. Why it is in liquid form? You have seen here the temperature of the liquids or energy possessed by the liquids is higher. So when this extra energy is released, the liquids will solidify. Okay, this process of solidification or consolidation take place either very slowly or quickly. If it take place quickly, then it results into amorphous solids. Okay, and if it takes large time, then what will happen? Large amount of energy is released with time, and the particles, the heat content present in the solids, that will reduces, and it leads to periodic arrangement, definite arrangement. Okay, same kind of particles settle down in definite region, that leads to crystalline solids. So class, here we have discussed the very basic and very important property of the solids. So due to periodic arrangement, anisotropy and less entropy, crystalline solids are of much importance. Now we are to see how we can study the crystalline solids in a logical way. I am saying that the crystals are the solids in which constituent particles are arranged in some definite order. So how you can study, how you can draw a meaningful logic, meaning or theory of these such kind of solids which are of much importance. So to study them we need a framework, okay, where particles are present, what is the angle between different planes where particles are situated. To study that thing we need a framework, that is framework network of points of different positions. The positions are lattice points, okay, and the arrangement network of lattice points is crystal lattice. So class, first point is crystal lattice. Crystal lattice. So I have told you lattice mean a network of locations, a network of locations or positions, okay. So crystal lattice which is periodic, देखो this network or location or position of particles is itself is periodic, and this is a hypothetical concept. This is a hypothetical, or you can say imaginary concept, okay. To understand concept, to understand arrangement of particles, in the crystal. So this network inside the crystal is called crystal lattice, okay. So as the definition justified, these are the location and positions where the building blocks, the particles which constitute the crystal, those are present. So what is present at these locations? Atoms or group of atoms, you can say molecules, these are present, okay class. Now what we call these atoms and molecules, these are bases, okay. So second thing is 2, this is bases. So these are simply atoms and molecules to understand. So if we have a network and we have atoms and molecules, when you put these atoms molecules on these locations, then crystal will be formed. So crystal structure is formed when you put the atoms molecules, when you adjust the atoms molecules in this network of points positions, okay class. So simply I can write the crystal structure, this is equal to crystal lattice plus the basis, okay class. So this is the equation, or you can say the definition of the crystal structure. So class, till now we have seen that crystal lattice is their network of points on which basis atom molecules are present, which gives rise to crystal structure. Now we will see the geometrical meaning or representation of the crystal structure. So basically we have, this is the fourth thing which I want to clear now, that is fundamental, or you can say them primitive translation vector, or simply vectors, okay, in case of a crystal structure. So we have here the locations where particles are present. It forms a crystal structure. So to have idea of the primitive vectors, you will see that this is a direction in which particles are present. This is another direction in which the arrangement of particles is definite. Okay, the line and the direction both are different thing. Okay, line is a geometrical concept. Okay, and direction, if you see, this is the same direction. You can draw infinite number of parallel lines along a direction. So this direction and this direction is same, and the arrangement of particles is same. Okay, mean to say, if you see the distance between these particles, let it is a, then another particle along this direction will be present at a distance a. Okay, so this is the unit distance which is repeated over and again to form crystal lattice, to form the crystal structure. Okay, now I am changing the direction. And you can draw infinite number of lines along this direction. So this dotted line is along a particular direction, and this gap here can be equal to a or may not be equal to a. Let I take it to be a general case. I am taking it to be b. Okay, so along this direction the particles are arranged at a distance b. So I am putting here another particle. Okay, I can put at the same distance b here another particle. Why? Because to form crystal structure we have to follow the very basic property, that is periodic arrangement and definite arrangement. Okay, so this is definite arrangement. Again the particle is present at a distance b. Okay, so here you can see in downward direction the distance of the particle, here the distance of the particle will be b, and if you see along this direction the distance must be a, otherwise periodicity and definite arrangement that will break down. Okay, so this is the thing. Now we are to see that what are fundamental and primitive vectors which form the crystal structure. So if I choose this point to be the point of observation, or I can say this is the origin, and along this particular direction I take this vector, the vector a, and this vector, the vector b, then vector a and b, these are primitive fundamental vectors. Okay, from which you can take the idea of any lattice point. Okay class, so if you want to take this point, then you can write this position of this point in the form of vector a and vector b. Those are primitive vector. So now let I take another vector. This is vector c. Okay class, this is vector c. Vector c is not primitive. This crystal structure, it is in 2 dimension. Okay class, it is in 2 dimension. Vector a and b are independent of each other, and vector c depends on a and b. Vector a and b cannot be formed using each other. Okay, but here you can see, you can write vector c as vector c, this is equal to 1 time of vector a plus 1 time of vector b. In the same way, if you take this point, and let I say that this is vector d, this is vector d, then I can write vector d as 2 times of vector a plus 1 time of vector b. So here you can have the idea of translation vector and the fundamental vectors. Vector c and d, these are translation vector. Okay class. So vector A and B, these are independent of each other. Okay, why independent? Because these vectors are taken along different directions, and in crystal structure direction is of much importance. Along this direction the particles are at a distance A. Okay, the arrangement of particles along this direction cannot be at a distance A. Okay, it can be, but A and B, these are independent of each other because directions are different. Along different direction, physical properties are different. Crystal structure form a matter, a solid which is anisotropic. Okay, so this mathematical concept, this imaginary hypothetical concept is very important. It is justified from experimental observations and change in physical properties with change in direction. Now come to the fourth point, come to the fifth point, that is translation vector. Okay, it is also a vector, but it is translation vector and different from fundamental vectors because it is translation vector is made up of the basic fundamental primitive vectors. See, vector C, this is combination of vector A and B. So vector C is non-primitive, getting me? Vector D is non-primitive. Okay, if I generalize this case, then I can write, I am not going with very basic things like definition of translation vector. You all have books and you can cram them from your books. Okay class. So here I am just to clear the very idea behind all these things, why we are taking this mathematical treatment is just to understand what is inside the crystal structure to make the concept easy. Okay, so here the fifth thing, that is translation vector, or this translation vector is an operation in itself, which I will discuss in the coming session. So it is represented by T. Okay, vector T, this is equal to I will write here n1 times of vector A plus n2 times of vector B. This is for 2D. If we have the lattice arrangement in 3 dimensions, then I will write one more here, n3 and vector C. This vector C and this vector C are two different things. Okay, here vector C is a combination of A and B. C is not linearly independent. Okay, but here it is in 2D. Okay, and this is in 3 dimensions. Vector A, B, C, these are linearly independent. You cannot write B in terms of C or C in terms of A. Okay, but their combination will represent a translation vector. So this is the thing. Now to take idea of this translation vector a little bit more, and why, what the values can be acquired by n1, n2 and n3, we will see here. Class C, this is the same lattice arrangement. We have particle here. Okay, this is, and I am taking this point, this lattice point to be origin, let I say, and we have a translation vector corresponding to this point. You will see it is passing in between the in between different lattice points. Okay, so if you see, this is vector T, I will write it T1. Okay class, and in 2D we have two vectors along this direction. Particles are arranged at a distance a, and in vertical direction the arrangement of particles is at a distance of b. So a and b are unit distance. So if you want to find out the position of second particle along this direction, then it will lie here, okay, at a distance of 2a, and other particle will be at 3a. Okay, in the same way, here the particles are at a distance b, so here particle is at a distance b, another particle will be at 2b. Okay, because of definite and periodic arrangement, you cannot find particle at this position. At this position particle is not there, because if particle is there, then it will become amorphous. Getting me? If particles are present at this position, it becomes amorphous. If particle is present here, then there is no any definite arrangement. So in crystal lattice, points are at definite position. So this vector can be written in terms of a and b, and here vector t1, this is equal to 1, 2, 3, 3 times of vector a plus 1, 2 times of vector b. So this is the thing. Here you will see the value of n1 is 3, value of n2 is 2, and it is in 2D, so I can take n1 to be 0. Okay, so from here you conclude that the value of n1, n2 and n3, it can be integer, only integer. Okay class? Okay class, the time of the lecture has been long, so I will discuss the sixth property, unit cell. What is unit cell? What is kind of unit cell in the next lecture? Okay, thank you class.